This is a quick slide about the rotation matrix properties. The first property is that all rotation matrices are orthogonal, okay, in which this means that the inverse of a rotation matrix equals its transpose, okay. So this tells us that it is very easy to calculate the inverse of a rotation matrix by just transposing it, okay. The second property is that any column or all columns are mutually orthogonal. So if you take any two columns of a rotation matrix and you dot product them, the dot product result must be 0, okay? Or also the rows as well. If you take any two rows, why is it so? Because it's a consequence or a corollary from the first property in which the rotation matrix is orthogonal. The rows are nothing but the columns of the transpose, okay? So that if the transpose is the transpose of a rotation matrix is itself a rotation matrix, so it makes sense that the rows and the columns are mutually orthogonal, okay? Notice here that we're not saying if you take a column, it's mutually orthogonal to all the rows. No, we're saying that the columns are mutually orthogonal and the rows are mutually orthogonal. The third property is that all columns and all rows are of unit length of any rotation matrix. The fourth property is that the determinant of any rotation matrix is 1. Okay. The fifth one is cool, and then you can prove it easily, but this is beyond the scope of this practical guide, okay, that the rotation matrices preserve vector length. So if you multiply or pre-multiply a vector by a rotation matrix, then the length of the rotated vector is equal to the length of the original vector. It doesn't change. Let me stop here and continue in the next video.